Welcome to this lecture on marine fuel composition and key components. I'm Dr. Sam Taufik, and in this session we will dive deeper into the chemical and physical makeup of marine fuels, the critical components that affect their performance, and the operational and environmental challenges associated with lecture objectives. The objectives of this lecture are as follows. First, to understand the chemical and physical composition of marine fuels. Second, to identify the key components and their specific functions. Third, to evaluate how the composition of a fuel affects engine performance and emissions. And finally, to connect fuel composition to international standards and environmental controls. This will give you a complete picture of why composition matters for both ship operators and regulators. Understanding marine fuel composition. Marine fuels are not single, pure substances. They are complex mixtures of hydrocarbons and additives, produced through petroleum refining. Their composition directly affects combustion efficiency, overall engine performance, emission characteristics, as well as how stable the fuel is during storage and how easy it is to handle. In short, the chemical makeup of a fuel determines whether it performs efficiently, pollutes heavily, or causes operational problems. Key chemical components. Marine fuels contain several key components. Hydrocarbons are the main energy carriers, from light, C10, to heavy, C70+, defining the fuel's energy value. Sulfur, inherent in crude oil, leads to SOx emissions, a major cause of acid rain and subject to strict regulation. Ash-forming metals like sodium, vanadium, and calcium appear as contaminants, causing wear and catalyst fouling. Asphaltons are heavy molecules that may cluster and form sludge. Water enters via condensation or delivery, risking corrosion and microbial growth. Cat fines, aluminum and silicon particles, from catalytic cracking are highly abrasive, damaging pistons and cylinders. These factors highlight why fuel quality management is vital for safe, efficient operations. Physical properties and operational impact. In addition to chemistry, several physical properties define how a fuel behaves in practice. Viscosity affects atomization during injection. Heavy fuel oil often requires heating to reach the right viscosity. Density impacts the mass flow rate and the effectiveness of fuel purifiers. Flash point is a key property. Marine fuels must have a minimum flash point of 60 degrees Celsius, as required by SILIS and ISO 8217. Pour point indicates the lowest temperature at which the fuel remains fluid, important in cold environments. Carbon residue reflects the tendency of a fuel to form deposits, which can reduce efficiency and damage the engine. Understanding these properties ensures that fuel is stored, handled, and burned safely and efficiently. Composition versus combustion and emissions. Fuel composition has a direct effect on combustion and emissions. High sulfur levels lead to SOx emissions, causing acid rain and corrosion. Low volatility fuels may not atomize properly, leading to incomplete combustion and soot formation. High concentrations of cat fines result in abrasive wear, damaging cylinders and pistons. Excess water content causes corrosion, steam generation, and overall operational instability. These examples show why even small differences in composition can have major consequences for performance, maintenance, and environmental compliance. Standards and testing. To control fuel quality, international standards are applied. The most important is ISO 8217, last updated in 2017 and 2024. It sets precise requirements for both distillate and residual fuels. Compliance is verified through laboratory testing using methods. ISTM D445 or ISO 3104 for viscosity, ISO 3675 or 12185 for density, ISO 8754 for sulfur content, ISO 3733 for water content, and ISO 10478 for cat fines. These standards and tests protect the engine, ensure compatibility, and guarantee compliance with international regulations. Fuel handling and safety. Handling marine fuels safely requires a set of best practices. Residual fuels must be kept in temperature-controlled storage, and often require heating and filtration systems before use. Operators must carefully monitor flash point and water content to prevent safety hazards. Documentation, especially through bunker deliveries, is essential for compliance. Finally, fuel stability and compatibility must be managed when switching between grades to avoid operational issues such as sludge formation or engine damage. Interactive knowledge check. Let's test your understanding with a few quick questions. 1. Which component in marine fuel is responsible for sludge formation? Is it hydrocarbons, asphaltons, water, or sulfur? 2. Which property indicates the risk of abrasive wear in engines? Is it flash point, cat fines, density, or ash. B. Which ISO standard defines marine fuel specifications? Is it ISO 9001, ISO 14001, ISO 8217, or ISO 45001? These checks help reinforce key concepts and can be delivered as quizzes using platforms like SCORM, Google Forms, or Summary. To summarize, the composition of marine fuel directly influences performance, emissions, and handling. Key components include hydrocarbons, sulfur, ash-forming metals, cat fines, asphaltons, and water. Important physical properties such as viscosity, density, flash point, and carbon residue are by international standards, like ISO 8217. Proper testing, safe storage, and careful grade transitions are essential to ensure both compliance and engine reliability. Ultimately, a strong understanding of marine fuel composition is critical for ensuring safety, efficiency, and environmental responsibility in the maritime sector. Thank you for joining me in this lecture on marine fuel composition and key components. I hope this session has helped you understand not only what fuels are made of, but also why their properties and impurities matter so much in practice. With my best regards, I am Dr. Sam Tofinj,